Chapter 1. Cloudlet. A cloudlet is a small data center placed close to users, designed for ultra-low latency interactive work. IEEE Edge drafts and vendor white papers describe cloudlets as compute placed near the last mile to support AR, industrial vision, and game streaming. In receipts, we see spec cards, port diagrams, teardown photos, and benchmark bars showing reduced round-trip times when sessions stay local. Mechanically, proximity shortens physical distance, peering removes hops, and a local cache or GPU node preserves session state without trips to a central region. Operating many cloudlets increases monitoring, hardware refresh, and power complexity compared with a single cloud region. And operator case studies document that distributed operations raise costs and staffing needs. The practical rule is simple. Choose cloudlets when sub-second interactivity and session affinity matter, and accept higher distributed operations overhead. Proximity wins for latency, but it demands an operations budget. Next, we'll explore a looser, more hierarchical alternative. Chapter 2. Fog. Fog computing is a layered continuum of gateways, routers, and microservers that pre-process data near sensors before cloud transfer. Vendors and industrial white papers repeatedly document gateways that sample, infer, and aggregate telemetry at the network edge to reduce bandwidth and improve responsiveness during intermittent connectivity. Receipts include bandwidth charts, field study diagrams, and gateway teardown photos that show constrained enclosures and specialized I/O. Mechanically, lightweight inference runs at the gateway. Heavier models execute on nearby fog nodes, and summaries or long-term storage move to the cloud, which cuts data volumes and keeps control loops local. Heterogeneous hardware across fog deployments complicates firmware management, driver supports, and security patching, so a hardened update pipeline is essential. Fog serves distributed sensor networks and bandwidth-limited sites best, but you must budget for device variation and lifecycle management. The payoff is reduced upstream load at the cost of careful fleet engineering. Next, we contrast that with massively distributed caching. Chapter 3. CDN. A content delivery network, or CDN, distributes cached content across many points of presence to accelerate global delivery of static assets. CDN operator documentation and performance reports show why static caching reduces origin hits, eliminates cold starts, and makes playback latency predictable for media and web assets. Receipts here include TTL and cache key diagrams, pop rack photos, and benchmark bars comparing origin versus edge cache response times. Mechanically, geography plus well-tuned cache keys and TTLs makes latency predictable, but dynamic, personalized responses and real-time game logic do not fit the pure caching model. Those cases require either edge compute integrated with the CDN or server-side session handling in nearby cloudlets. Synthesizing the three models, cloudlets deliver low latency and stateful sessions for interactive workloads. Fog provides hierarchical pre-processing near sensors for bandwidth-constrained IoT, and CDNs excel at massively scalable static delivery with minimal per-request compute. This synthesis highlights a practical trade-off. As workloads become more stateful and privacy-sensitive, we lean toward cloudlets or on-prem options and away from pure CDN caching, which directly affects placement and orchestration decisions. Chapter 4. On-prem. Keeping compute on-prem is a hard counterbalance because local processing buys data locality and compliance but shifts scale and maintenance burdens inward. Regulated industry case studies show on-prem deployments reduce external data egress and satisfy strict residency rules, yet they require capital expenditures for redundant power, hardware, and networking. Mechanically, on-prem gives you full control over network topology, physical access, and latency inside a campus. But matching CDN or cloudlet geographic reach requires replicating infrastructure across regions. Receipts include compliance checklists, rack photos, and internal network diagrams that document these trade-offs. The practical lesson is that on-prem is ideal when policy or privacy mandates local processing, or when predictable intra-site latency matters, while hybrid models remain necessary for global reach and elastic demand. Local control improves privacy posture, but it puts the ops burden squarely on your team. In the next chapter, we cover how to orchestrate across all these choices. Chapter 5. Orchestration. Orchestration is the operational glue that makes cloudlets, fog nodes, CDNs, and on-prem systems work together under real constraints. Orchestration vendor docs and case studies show schedulers that understand latency objectives, data residency rules and cost ceilings, and control planes designed for intermittent connectivity. Receipts here include control plane diagrams, signed artifact flows, rollout semantics, and health probe charts from real deployments. Mechanically, a scheduler must translate policy into placement while tolerating heterogeneous endpoints and intermittent network links, and a secure pipeline must deliver signed artifacts and configuration to each node. Real deployments prove policy matters more than raw speed. A placement that saves milliseconds but violates privacy or explodes ops costs is worse than a slightly slower, manageable option. Map each workload against 3 axes: latency sensitivity, data locality or privacy requirements, and operational budget. Then choose the simplest architecture that satisfies those axes. As a practical test, deploy one representative service. Measure its P95 client-to-node latency and tally where session state lives. Compare those measurements against your residency rules and a week of operational touchpoints. If this framework helps, iterate and share which trade-offs surprised you most.